Hey folks, welcome back to Combo Class, where today I want to tell you something really cool. I was playing around with prime factorizations and doing experiments on numbers, and I discovered a very interesting pattern. And when I did look up if any other mathematicians had worked on this in the past, they had, but to a very limited degree. There was not much information about it, and I was able to prove new things that no human may have ever proved. That is just a simple variation on taking the prime factorization of a number. So today, let me take you through some iterated number sequences to see what I was able to find and prove about an interesting pattern, as well as some strange variations and extensions to it. It can be interesting to take some sort of rule for a sequence, like if I had x squared being my output of some sequence, and then iterate what happens as I continue plugging a number back into that beginning. Like in this case, 1 would stay at itself, squared, squared, squared. 2 would go to 4, then 16, then something large. But I'm most interested in sorts of sequences that, for one, have the chance of growing or shrinking in an unpredictable way. Like if you look at a certain element, you can't tell from a quick glance if it's going to get larger or smaller. And also sequences that, like that squared one, are base independent, that don't rely on traits related to the base 10 system we write digits in, but some fundamental trait within them. And one very fundamental trait within numbers are the primes that make them up. You can break numbers down into prime factorizations that are like their elemental structure in a way. Like 18 multiplicatively can be broken down into a 2 to the first power and a 3 to the second power. And there's no way to break those primes smaller. Now, there are interesting things that we could do with this prime factorization to create some function that changes a number. And when I was playing around with that general concept, prime factorizing a number, changing something about its structure, going to whatever number that creates, and possibly iterating the process from there, seeing where that number goes and where that goes. Playing around with different ways we could mutate this structure, what I called Primeglitching, and I found that most of the ways of mutating it, like if I turned these into multiplication and kept multiplication in between, would have a pretty predictable structure. All the prime numbers and the number 4 would stay the same, all other numbers would shrink. Now today, we're going to look at a pattern which is similar and equally simple, but which contains a lot of surprises. So our main pattern is going to be, we take a number, like let's say 60, we look at its prime factorization with each exponent written in, including the first powers, and then we take each of those, and instead of having them as exponents, we add them, like 2 plus 2 there, 3 plus 1 there, and 5 plus 1 there. We could also describe what we're doing mathematically as taking the product of each prime that can divide a given number individually added with the highest exponent that prime to that power could also divide the given number. Now, based on either of those definitions, which end up being the same, 60 leads to the number 96. It grew a little bit. And we can find some general patterns right away about certain types of numbers that we know will definitely grow or definitely shrink. For example, the number 30 has a similar prime factorization to 60, but the 2 is just to the first power. This number only has first powers on its primes in the prime factorization, and that sort of number is known as a square-free number because this implies that no square number can divide it. Well, any square-free number we know will definitely grow under this process because the first powers of each of these primes are themselves, but if we add that exponent, we're now at one more than each of those primes, which in this case multiplies out to give us 72. Now, in the case of 60, that's actually pretty similar because we had 2 to the second power, but these ones were just first powers. And that type of number, where all of the primes in the prime factorization, apart from a single case of 2 to the power of 2, have a first power, will definitely grow as well, because 2 to the power of 2 is the same as 2 plus 2, so that element neither grows nor shrinks it. And if there are other primes to the first power, those elements will grow it, and we will end up resulting in something larger than the original. As a flipped sort of that rule, if we look at a number like 225, which has a prime factorization of 3 to the second power times 5 to the second power, we know that this sort of number will definitely shrink because all of the powers within it are at least the second power. And if we had a single case of 2 to the second power, that wouldn't change things either because that would be 900 now. That element wouldn't grow or shrink it. It would still just be 4, 2 plus 2. And these elements would certainly shrink it. And so anytime we see a number where any of its exponents are at least the second power, apart from the number 4 itself, which just would be 2 to the 2 and doesn't grow or shrink, leads back to itself. Any other combination of prime factors, including that if we want, but at least some others, that have the second power or greater for all of them, will certainly shrink. In this case, resulting in the number 140 as opposed to 900. And without that, this would have been 225 turning into 35. Well, let's take a look at two different numbers that look different at first, 630 and 1050, but which actually have pretty similar looking prime factorizations. They each have a 2, 3, 5, and 7, but in this case, we have a second power on the 3, and all the others are first powers. And in this case, the only one with the higher power is the 5, having a second power. Well, when we do that function of turning each of these into the sum of the elements and then multiplying them all together, 630 results in 720. It grows a bit, whereas 1050 results in 840. It shrinks a bit. Here, the amount of shrinking that happened from that power was less than the amount of growth these all contributed together, and the number grew overall. But in this case, the amount of shrinking from there overweighed the amount of growth of those ones, and it ended up shrinking overall. So it can be a bit unpredictable when these numbers with the mixed sorts of prime factorizations are going to grow or shrink. Now, the most interesting traits come when we take a number, look at its result, and iterate the process, looking at the result of that and the result of that and seeing where it goes. Starting small, the number 1 has an empty prime factorization, so we could either see that as crashing the system and not working within it, or we could see it as 1 being its own fixed point, because 1 is what's known as the empty product. When you multiply nothing together, sometimes you revert to the multiplicative identity, 1. So I like to think of 1 as leading back to itself. And somewhat similarly, if we look at where the number 2 goes, well, the number 2 has a prime factorization of just 2 to the 1. So we could say that that goes to 2 plus 1, 3, which has a prime factorization of just 3 to the 1, which goes to 4, which has a prime factorization of 2 to the 2 and leads back to itself. So 2 and 3 lead to 4, which is essentially a fixed point or cycle of length 1 that leads directly back to itself in a pretty expected way. And any number larger than 4 will not lead back to this cycle because it's going to have some element that either must be some prime larger than 2 or 3 plus its exponent, which will result in larger than 4, or have multiple components that are multiple things that are larger than 2, because 2 plus 1 would be the minimum, multiplied together. So only 2, 3, and 4 lead to this fixed point. What about slightly larger numbers? Like if we look at the number 7. Well, 7 has a prime factorization of 7 to the 1, so that goes to 7 plus 1, or 8, which has a prime factorization of 2 to the 3. 2 plus 3 leads us to 5, which has a prime factorization of 5 to the 1. That adds to 6, and 6 is 2 to the first times 3 to the first. We have 2 elements there. 6 leads to 2 plus 1 times 3 plus 1, which is 12, which has a prime factorization that's somewhat similar looking to 6, 2 squared times 3 to the first. And now we have 2 plus 2 times 3 plus 1, leading us to 16, which has actually less elements in its prime factorization than before, because 16 is 2 to the 4th power. And when we add 2 plus 4 there, we go back to 6. So this is a little cycle of length 3. 6 leads to 12, leads to 16, and back to 6, and etc. And any number that leads to one of these will end up falling into that infinite cycle of length 3. So all of the whole numbers from 2 through 9 either lead into this little shrub of 2 to 3 to 4, or into a larger tree that feeds into that cycle of 6 to 12 to 16 and back. But what about other numbers larger than a single digit? 10 does something a little bit different. Looking at the number 10, that has a prime factorization of 2 to the first and 5 to the first. Now we have a 3 times 6, giving us 18. 18 is a 2 to the first times a 3 to the second. Now we have a 3 times a 5, giving us 15. 15 is a 3 to the 1 times a 5 to the 1, giving us a 4 times a 6, that is 24, and 24 is 2 cubed times 3 to the first. This gives us 5 times 4, leading to 20, which is 2 cubed times 5 to the 1, and that leads us to 4 times 6, which is back to 24. So 24 and 20 lead to each other in their own cycle of length 2. And if you investigate the first, say, 50 numbers, you'll find that all of them lead to either some cycle of that 6, 12, 16, or the cycle of 20 and 24, or they're already in that little shrub of 2, 3, and 4 on their own. But the pattern gets deeper if we look beyond 50 numbers. If we look at the number 58, we'll see something interesting. 58 has a prime factorization of 2 to the first times 29 to the first. That leads to 3 times 30, or 90. 90 has a prime factorization of 2 to the first times 3 to the second times 5 to the first. Now, when we apply our transformation to this, we get 3 times 5 times 6, which is 90. 90 leads back to itself as another fixed point, like 4 was, but in a much more interesting way, because unlike 4, which just created itself by the exponentiation being the same as the addition, here the elements create each other. The 2 to the 1 leads to one of the factors of 3 we need, the 3 to the 2 leads to the factor of 5 we need, and the 5 to the 1 leads to the factor of 2 we need and the remaining factor of 3 we need, because that's what this 6 breaks down to. Now, it turns out there is one other fixed point around this size, the number 120, which has a prime factorization of 2 cubed times 3 to the 1 times 5 to the 1. And similar to this case, it builds itself in a somewhat surprising way. The 2 to the 3 becomes the 5, the 3 to the 1 becomes 2 of the 2's we need, and the 5 to the 1 becomes the remaining 2 and the 3. Apart from the shrub of 2, 3, 4, numbers will either lead to some tree relating to 6, 12, 16, to 20, 24, or to one of the singular fixed points 90 or 120. But this amount of numbers is practically nothing compared to the infinite number line. So how do we really know that these are the only fixed points or cycles that exist? Could there be some case where some really large number led back to itself, or looped with another, or led to some cycle of a longer length? I did test some larger numbers too, to see some examples of what happens further up the number line. For example, I tested 8 different 50-digit numbers that I semi-randomly generated from clusters of pi's decimal digits, and each of these 50-digit numbers in 10 to 20 transformations each led to one of the expected cycles. I also got some help from my friend Stick, who did some programming and tested some numbers, all of them up to 1 million, and showed that up to 1 million, all of the numbers lead to the expected cycles. This also gave me some other cool types of information, like, for example, in that size range, up to 1 million, approximately 28.5% of the numbers shrink after their first transformation, approximately 71.5% of them grow, and at that size range, we've gotten to the point where approximately 0% of them stay the same, because those are only those fixed point numbers that do that. Now, if you have a type of number and you look at how often it occurs among natural numbers for larger and larger stretches of number line and see what that approach is, you get a trait called natural density. And if we looked at the natural density of how many numbers will grow under their first transformation, although I'm not sure if it would be more or less than this 71-ish% figure we approached, I do know that it would be at least 60-ish%, or to be precise, at least 6 divided by pi squared proportion of the numbers would grow under their first transformation. I know this because 6 divided by pi squared has been proven as the natural density of square-free numbers, which we can recognize as only having first powers in their prime factorization and being numbers that we know are among the type that would grow under their first transformation. So with a strange, surprising connection to circles here, we find that at least 6 divided by pi squared proportion of natural numbers must grow under one transformation of this process. Earlier in my investigations, I looked up these fixed points I'd found, 4, 9, 120, as well as some other related sequences of numbers on the classic website, the OEIS, Online Encyclopedia of Integer Sequences, where often I've looked for a pattern and discovered that other people have done research, perhaps even named it, and it can give me more clues about the phenomena. Now, in this case, I didn't find anything with those terms in their sequence on the OEIS. However, a little later in my investigations, I searched these terms, 490, 120, as a general Google search, and it did lead me to the OEIS, leading me not to a sequence that contained those exact numbers in a row, but to a sequence that had those numbers as a string within its comments. This sequence showed how many steps each number would take before it encountered some number for the second time, meaning it had fallen into some fixed point or cycle. And in the links to this sequence, I found another sequence here that showed where each number led after a single transformation of this process. And those were the only two sequences I could find related to this, and they did not have a lot of notes about them, but the notes they did have were quite useful. Like, now somebody here had apparently verified that up through 10 to the 8th power, which is 100 million, every number does fall into one of those expected cycles. Although there weren't any concrete proofs of that, which we'll get to in a minute. However, the coolest thing I found on these pages wasn't just the further tests of the same hypotheses I'd already had. It was an alternate phrasing of the type of transformation we were doing. Another way you could describe this original process that we'd been looking at this whole time. And first, let me show you how sometimes we might ask a question about a number's prime factorization. Let's use good old 18 as an example. And a question or transformation we could apply to that might result in the same answer as some other question that is fundamental to numbers in its own way, revealing certain possible fundamental structures in the question we had been discussing. And one example of that is if I were to take a prime factorization and do sort of the opposite of what we'd been doing so far. So far we'd been adding within each of these components and then keeping multiplication between them. But what if we multiplied between the components instead and then put addition between them? Well, 2 times 1 plus 3 times 2 gives us 8, which isn't only the result of applying this possible transformation, it also turns out to be, in general, the sum of the prime factors of our original number. Multiplicatively, it had 1 2 and 2 3s, and if we add those up, we get that. And so sometimes we can look at one way of phrasing some sort of function or transformation that turns out to secretly be identical to another question within number theory. In this case, this flipped version telling us about the sum of each prime factor in the number. So what about the process we had been doing, where instead of exponentiation, we turned each of these into addition, but we kept multiplication in between? Well, in this case, it does turn out that there is a slightly less simple, but still fundamental in its own way, alternate phrasing of what this will result in. If we look on the OEIS, we'll see a note from someone a few years ago that just says the result of this is the sum of the power-free parts of the divisors of n. And what does that mean? Well, if we look at all of the positive factors of 18 as opposed to just the prime factors. And then we prime factorize each of those, deleting any of the exponents in its prime factorization that has an exponent larger than 1, and the power-free part of a number is the product of only the primes that just have a first power in its prime factorization, and that gives us, in this case, a 1, because 1 is the empty product when we have nothing we're multiplying together, as well as this case, or in these cases just gives us the number itself, and in this case too, because each of its prime factors were just to the first power, so multiplying them together gives itself. In this case, just has 2 remaining. And we noted that if we add up each of the power-free parts of a number's divisors, we get something interesting. Here we have 1 plus 2 plus 3 plus 6 plus 1 plus 2 is 15. And 15 is the result of applying our original type of transformation to 18, where we took its prime factorization, added within the components, and kept multiplication between. And that will be true for any positive integer that we can look at this alternate definition that is not necessarily easier and doesn't have any more information I could find about its iterated function, but is just cool by showing us another way connected to the aspect of number theory when we look at all the divisors as opposed to just the prime factorization, and somehow we get the same result. It's the other pattern in disguise. But even with all this additional data and this alternate definition, I still wasn't able to find a proof that these fixed points and cycles that we knew were the only ones on the infinite number line. Testing larger finite stretches of number line would never be able to give us a proof about that question related to the infinite amount of natural numbers. However, there are other ways you can prove things, and I decided to see if I could prove whether any of these fixed points or cycles were the only ones of their type on that infinite number line. Now, I did discover some really cool things, although what I'm about to show you isn't using technical formal proof language. It's going to be more like series of logical deductions that let me conclude certain cool statements. And if any of you want to try either polishing up these proofs by making them more formal, or finding your own similar proofs that are more concise or shorter ways of proving these things, that would be awesome to hear about in the comments. First, let me show you some general patterns I was able to justify about where numbers will lead under this process. First of all, it can be helpful to create nicknames for the type of things in our mathematical process. So let me nickname a few things. If this number goes to this number, let's call this the parent of that number, and this the child of that number. And if there's a number that somewhere in the parents of parents of parents of a number led to it at some point, let's call that a descendant of the number. And if a number eventually leads to something else, let's call that an ancestor of a number. Now, within each number, there are different, what we'll nickname different components, and those are each distinct prime raised to an exponent. Like, let's say the classic number 18 has a component of 2 to the first power and a component of 3 to the second power. And we know this component will help it shrink and that'll help it grow. And if we want to know how much they will add up to with that growing versus shrinking, we can look at how they change multiplicatively. Like 3 squared is now becoming a 5 when it would have been a 9. So it's like multiplying the quantity by 5/9. That's shrinking. But 2 to the first power is becoming a 3 when it would have been a 2, and that's shrinking it. Now when we multiply these together, we get 15/18, and we can see exactly how much multiplicatively that number would grow or shrink if these different terms of how much they each changed it multiplied to less than 1. We can also note that if a number has a certain amount of odd prime factors in it, prime numbers that are to the first power in its prime factorization and aren't specifically 2 to the first power, the only even prime, that this number's child must contain a power of 2 that is at least as large of an exponent as the number of odd prime factors of the parent, like at least 2 if these were contained in it, because each of these must contribute a factor of evenness in a way. Any odd number plus 1 is twice something, and those will each create at least one level of evenness that we'll have in the child. Each number will lead to a single child and could potentially have multiple parents that lead to it. The only whole number larger than 1 that doesn't have any parents is 2, and the only whole number larger than 2 that doesn't have an infinite amount of ancestors that'll eventually trickle down to it is 3, and 4 is ambiguous in a way depending how you consider a fixed point potentially being its own parent and its own child. 4 is a good example of how fixed points can be alternately described as numbers that are their own parents and their own children. 4 gives birth to itself and gave birth to itself. And similarly, numbers that are in cycles of any sort could be alternately described as the numbers that are their own descendant or their own ancestor at some point. Every number larger than 4 will have an infinite amount of ancestors that will trickle down to it in trees, and if a number appears in its own tree more than once, we know it's in some sort of cycle. All right, folks, you ready to see some proofs that, oh my god, some proofs that I might have been the first person ever to demonstrate about numbers? Let's begin with the case of a fixed point, which are numbers that lead directly to themselves, or we could say numbers that are their own child and their own parent. Now, for a number that leads back to itself, could that number ever have just a single component? By component meaning each prime to some exponent within its prime factorization. Well, we know this works in one case, the case of 2 to the 2. But since we can judge a number's entire growth based on multiplicatively how much each component grows or shrinks it, and this is the only single component that doesn't grow or shrink, we know that any number apart from 4 itself would need multiple components to lead back to itself, because it would need at least one element that grew it and at least one element that shrank it to balance out. This lets us know that this number would have to have a power of 2 within it, because either it had a power of 2 to the first, which was the growing component we needed, or it needs some other growing component, which would be an odd prime to the first power, which would contribute to a level of evenness that, if the number leads back to itself, requires some power of 2. So we know this number has some power of 2 within it. Now let's check how large that power of 2 could potentially be. Could this number have a power of 2 larger than 3 in its mix? Now here's the thing, a power of 2 to 4 or greater would shrink a number by at least 2 plus 4 over 2 to the power of 4, which here equals 3/8. And to counterbalance that amount of shrinking, we would need growing elements that were at least 8/3 multiplicatively. But we can't have any 2 to the first powers in that case, because we already have 2 to a higher power. And if we have a 3 to the first power, that does help with growth a lot by a factor of 4/3, but it also adds 2 of the even factors that we know we have. Any power of 2 larger than an exponent of 3 will shrink a number by 2 plus the exponent divided by 2 to the power of the exponent, which gets more and more shrinkage as we go along. So when this is larger than 3, we will need more amount of odd primes to counterbalance the effect, especially considering that some of these odd primes count as 2 or more in a way, like 3 to the first power contributes 2 factors of evenness that were allowed, whereas some other odd primes only contribute 1 factor of evenness, but those ones might help with the growth less so. If we try and stack odd primes to counterbalance a 2 to the a with the a larger than 3, we will end up needing so many odd primes, we should have had a larger exponent to begin with, which is a contradiction. Now that's one of the parts of the proof that's less formal. If any of you want to help formalize it, leave a comment about how you could phrase this better. But I do have the logic behind the statement that we hit a breaking point once 2 is at a high enough exponent that we couldn't have enough odd primes to counterbalance it without contradicting what our original exponent was. We've basically eliminated the case of where 2 is a power higher than 3. We've already demonstrated this number would need to have some power of 2 in it, so we're left with 3 cases: that it has a 2 to the power of 1 somewhere in it, that it has a 2 to the power of 2 somewhere in it, or that it has a 2 to the power of 3 somewhere in it. Now in this case where the number contains a 2 to the power of 2, we do know there is one fixed point that fulfills that, the number 4 itself, which is just that as its prime factorization. But for numbers apart from 4 that contained that, we would need at least one growing element and at least one shrinking element, and we would note that we can only have a maximum of 2 odd primes because those would come back to the power of 2 there, and we already used up 2 to a power, so any growing element has to be an odd prime. Now, if we need a shrinking element somewhere in there, we would need something that shrinks it at least as much as 3 squared, which shrinks by a factor of 5/9. All other shrinking components shrink it by a larger factor than that. And so to counterbalance that, we would need growing elements that are 9/5 or larger multiplicatively, but this number already used up a 2 to the something, so all of our growing elements have to be odd primes, and we can only have up to 2 levels of evenness that are recreated. If we have a 3 to the 1 and some other power that shrunk, well, this number already creates both levels of evenness because it makes 4, and so that on its own isn't enough to counterbalance whatever other shrinking element we would have had. And let's say we had that 3 to the 2 as our minimal shrinking element and 2 other odd primes. Well, even at the case of the next 2 odd primes that grow it as much as we could in this scenario, that is not enough to counterbalance that. And so a number of this form we know couldn't be a fixed point unless it only had that prime factorization and was the number 4. Now in this case where the number contains a 2 to the first power, that will create a 3 to some power within the prime factorization, and it can't be a 3 to the first power, because if it was a 3 to the first power, that goes to 4 in our transformation, which creates 2 levels of evenness, not 1. So this 3 needs to be raised to a power larger than 1. And if it was raised to a power larger than 2, that would cause way too much shrinking for up to 1 odd prime to counterbalance. So the only possibility would be a 3 to the second power, which does cause a lot of shrinking by a scale of 5/9. This one causes a bit of growing by a scale of 3/2. And we would need 1 more odd prime to counterbalance all of this. We can't have more than 1 odd prime or we get extra levels of evenness. Now, if the odd prime is something larger than 5, the amount of growth won't counterbalance this. All the multiplicative factors won't multiply to 1. However, if it is 5 to the first, that gives us an amount of growth of 6/5, and multiplying all these, we do get 1. These do create each other's factors because this lines up exactly with the fixed point 90. So how about this case where the number contains a 2 to the third power? Well, this adds to 5, so we need a 5 to some power within the number. It can't be a 5 to a power larger than 1, because if we look at how much that would shrink it, multiplied by that already shrinking it by a factor of 5/8, that 3 odd primes would not be enough to counterbalance that, and we only can have up to 3 odd primes here. And so we need a 5 to the 1, and a 5 to the 1 will create a 6, which is a 2 to the something and a 3 to the something. So we do also have a 3 to the something in the mix there. And if we analyze if that could be a larger exponent than 1, we'll similarly find that would shrink it way too much to include a couple other odd primes and try and counterbalance that. So we need a 3 to the 1 if it's gonna work, and it does. This lines up with the number 120. But this is the only case of 2 to the third power that could work. And so overall, that's my sloppy proof that these are the only fixed points that exist in this sequence. Now, how about cycles of length 2, where it's a little trickier to prove things about because these numbers are not creating themselves with the new prime factors. However, they are creating each other. In a 2 cycle, each number is each other's child and each other's parent. With a cycle of 2 numbers leading to each other, they can't be equal sizes or they'd both be fixed points, and they can't both grow overall or both shrink overall, or they wouldn't lead to each other. We must have 1 number that shrinks overall and 1 number that grows overall that lead to each other. Let's nickname n the number that must grow overall into some number m, which is our number that must shrink overall back to n. We know that n must contain some odd prime to the first power because it can't just be the number 2 to the first power, given that 2 itself is not in a cycle of 2 numbers, we can easily verify, and 2 times any other elements would either contain odd primes or shrinking elements that would require a bunch of odd primes to make that a growing element overall. So somewhere in n's mix, it has at least 1 odd prime to the first power, meaning that somewhere in m's mix, it has a power of 2 to at least 1. So let's look at some options of what m's power of 2 could be. If m contains a power of 2 to the first somewhere in it, that means that n has a maximum of 1 odd prime, and that n has a 3 to some power somewhere in it, which this creates. And so if n's 3 to the a is some exponent larger than 1, then n would have to have a shrinking component that shrinks it by at least the amount of 3 squared, which shrinks by 5/9. And if we wanted to counterbalance that, because n is supposed to grow overall, the maximum we could counterbalance that would be a 2 to the first power to grow, and then a single odd prime to grow. And it can't be a 3, we already used that. So let's say we had a 5 to the first power. Now if this was precisely the second power on the 3, this amount leads back to itself. This is equal to our fixed point of 90. And we know we're not looking for fixed points here because we need one number, which was n, which grows. And if this contained 3 to the power of more than 2, that would definitely be too much shrinking for a single 2 to the first power and another up to 1 odd prime to counterbalance and make n a growing number. So overall, m can't have just a 2 to the first power. It's interesting, these numbers tell us about each other. Now let's say that m has a 2 to the second power. Well, in that circumstance, n can have a maximum of 2 odd primes, and it must also have a 2 to the power of at least 2, because that will be self-created there. And so a 2 to the power of more than 1 exists somewhere in n, and m must still shrink overall, despite this element not growing or shrinking. So it must shrink by an element that is at least shrinking it as much as a 3 to the 2 would, and that shrinks it by an element of 5/9. And so we need at least the opposite of that amount of growth for n. Now since n can't have 2 to the first power, the only elements that could help it grow would be odd primes to the first power. And if we had a 3 to the first power, that would use up both levels of evenness that it would create. So we could either have something like that, or something where we had that 2 and then 2 other primes that were under what are known as singly even numbers, numbers that can only be cleanly divided by 2 twice. 7 doesn't even work for that, because 7 to the first power would make an 8, which is way too many 2's there. We'd have to go all the way up to 13 to the first power, and neither of these cases is enough growth to offset the amount of shrinking that whatever m's shrinking component would be would cause. Therefore, m can't have a power of 2 to the 2 in it. Now, if m has a power of 2 to the 3 in it, that means that n must contain a 5 to the something somewhere within it. If this exponent was larger than 1, we would have 2 shrinking elements that overall had this cycle shrink by at least 5/8 times 7/25, which would be the minimal case of this shrinking. And that would be way too much to overcome the amount of odd primes we could tuck in here, knowing we have a maximum of 3, and the amount of odd primes we could tuck in here without getting a larger power of 2 in there, which caused even more shrinking. But what about the case where 5 was to the first power? Well, if 5 is to the first power, that creates 1, 2 there, as well as a 3 to the something. And if this exponent on the 3 was larger than 1, then we would have too much shrinking for the amount that up to 3 odd primes could grow it. And so this has to be a 3 to the first power. This 3 to the 1 creates a 2 to the power of at least 2 in its child, which is n here. And if we had a 2 to the power of more than 2 here, that would be another shrinking element, and we wouldn't have nearly enough growing elements to counterbalance it. So it would have to be a 2 to the power of exactly 2. And if we check this case, it does work. This is when n equals 20 and m equals 24. But that will be the only case where a cycle of 2 can have the larger number contain a power of 2 to the third. So what about the cases where m contains some power of 2 larger than 3? Now in any of these cases, we'll have an amount of shrinking that's at least 2 plus 4 divided by 2 to the power of 4, which we've seen is 3/8 amount of multiplicative shrinking. And if we want to counterbalance that with elements of n that add growing elements, we would need a ton of odd primes. However, n can't have very many odd primes, because if we have too many of those, that means we need a higher power of 2 there, which means we need even more odd primes to counterbalance it, and back and forth in sort of a feedback loop. And m also can't have many odd primes, because if it had a bunch, that would mean n also needed a 2 to the power of something that was a shrinking element, and we'd have this problem going both directions. And that is my really sloppy proof that we can't have any 2 cycles that contain the larger number having a 2 to the power of more than 3, and that in general, the only 2 cycle that exists should be 20 to 24. Now, what about cycles of length 3? Let's note that a cycle of 3 numbers can either go grow, shrink, shrink, or grow, shrink, grow. In some order, we know that there's going to be a growing element that leads to a shrinking element that leads to an element that could be either type theoretically. For cycles of length 3, although I was able to kind of logically deduce with a long chain of testing different scenarios, like how many of a certain type of exponent something could have, or the maximum count of exponents total, or traits like that, I was able to deduce that the cycle we know of length 3, 6, 12, and 16 should be the only one, but I wasn't able to quickly put together a full proof of that. And I realized this episode is already so long, and I've spent a lot of this month working on this problem, so I decided we'll come back to our proofs of the 3 cycles either in some live stream or bonus video on my bonus Demotro channel, or maybe some of you will try and solve that on your own like a fun puzzle. Now, the way I think we could approach these further proofs is based on a few factors that each cycle length, like say a cycle of 7 different numbers, seems to have some sort of limit or breaking point in terms of the highest amount of shrinking a single component in it can do. Like a cycle of length 6 might not be able to have a 2 to the power of 1,000, because that would shrink the number so much that we would need such an extraordinary amount of growing elements, which would need to contain a lot of odd primes to the first power, since each growing element does not grow it as much as each shrinking element shrinks it, that we would end up needing to stack an even higher exponent of 2 or even higher shrinking amount than we had originally assumed, leading us into sort of a feedback loop of the higher powers of 2 you have, the more odd primes you need, which lead to an even higher power of 2, and etc. Now, with that, I think there could be some way to not only prove the 3 case somewhat elegantly, but also prove in general that no other cycles exist, which, although I haven't proven myself yet, I do suspect cycles at least would have to be rare. If any of you want to polish up this proof or find any better proofs of your own, you could use maybe variables. Perhaps you could say that In this proof, we're looking at the times where the exponent of 2 is a number that is some constant multiplied by the cycle length, or the cycle length to the power of some constant. Now, if any of you try to prove this yourself, be careful about a few things. If you really want to prove that all numbers end up falling into one of these cycles, you not only have to prove that there's no other cycles, you also would need to prove that no numbers spiral upward toward infinity, that there are no numbers that continue growing and growing until they're arbitrarily large. So, with those mix of factors, good luck proving some interesting things. Leave a comment if you do. And although that's all the proofs we're going to cover today, that's far from the end of this episode. Now, beyond proofs using positive integers, we can extend this further. Some of you may remember that near the beginning of grade -2 of combo class, that we're now near the end of, I showed that numbers beyond whole numbers can have prime factorizations. If we extend prime factorizations to include things like negative exponents, it can capture every rational number with a prime factorization. For example, the number 1/2 is sort of secretly 2 to the negative first power. So what happens if we expand which inputs we allow and let in some other rational numbers and see how they transform? We could theoretically take a number like 0.9, which has a fraction that represents it, 9/10, and look at that prime factorization as 3 to the second power, making up that numerator, and 2 to the negative first power times 5 to the negative first power, making up the denominator. Now, if we applied our original transformation to that, that gives us 3 plus 2 times 2 minus 1, or, 2 plus -1 is the same as that, and 5 minus 1, which leads to 5 times 1 times 4, which equals 20. And we know the number 20, if we iterate this process, leads to that loop with the number 24. So we could say that 9/10, that rational number, leads to the 2024 cycle. We will notice also that this gives numbers an infinite amount of parents now, where the number 20 not only has the finite amount of positive integer parents that we met before, but also not only has 9/10 as a parent, but also an infinite amount of other parents. Like, one way of constructing an infinite family of parents for the number 20 would be to start with 20 being 2 to the second power times 5 to the first power, and then noting that if our denominator was some other prime times 1 less than that prime, the prime factorization and our ensuing rule would make that 7 minus 6 and add just a times 1 to there. Some numbers, like 1/2, which we can prime factorize as 2 to the negative first power, would lead us to the number 1, which, like we said, we could either treat as it crashing the system or as it being its own fixed point, depending how we treat the empty product. And some numbers, like 1/4, would lead here to 2 to the negative second power, and 2 plus -2 is 0, so that would lead to 0, and we could either consider 0 as crashing the system or as having an infinite amount of factors, leading it to grow to the size infinity and then crash at the number infinity, if we defined it that way. In any case, an infinite amount of rational numbers will lead to 0, as well as 1, as well as, if we look at fractions like 1/8, that's 2 to the negative third power those add to -1. We now are able to have negative versions of integers, and we have to figure out the rule of how we're going to treat negative signs in prime factorizations. Let's just say that when we iterate a process from a number, if it's negative, we put the negative sign to the side, prime factorize the typical absolute value of the number, and then apply that negative sign if it was there, meaning that -1 here would also either crash or be its own fixed point, and we would also have other matching fixed points and cycles that were negative versions of all of the positive ones we'd met, like -20 going back and forth with -24. And we can even note that apart from some numbers leading to 0, the only other fixed point cycle type things that this new process of allowing rational numbers would allow would be negative versions of positive integer cycles or fixed points that already existed. Because any rational number, if it was a fraction in terms of needing some sort of negative exponent in its prime factorization, would still lead us to some integer, sometimes negative. So after just one transformation, any rational number, which we can now allow in our system, leads to some point that would lead us to something else we already have in our system, with us just needing to throw the negatives in there as well. Now that's not the furthest. We can take the idea of extending prime factorizations. To anyone who saw my episode earlier this grade, you would have noticed we incorporated things like square roots and cube roots as well. Because, the principal square root of 2 is 2 to the power of 1/2. So why can't we put 2 to the power of 1/2 into our formula? Now, we could plug in all sorts of numbers. Like if we look at the number, the number 3, oh my God, the number √3 over 5, then that is an acceptable input with our new system, because we can prime factorize that as 3 to the power of 1/2 times 5 to the power of -1. And then when we apply our transformation, that sends us to 3.5 times 4, 14. So wherever 14 ends up leading us, this number √3 over 5 will. And now we have whole new families that we could introduce as inputs to our system. And as an example of how it can be kind of fun and unpredictable where certain numbers go, let's look at some different variations on the number 6. We know 6 itself goes to a cycle where we end up going from 6 to 12 to 16 back to itself. And the number 1/6 would be 6 to the negative first power, or in other words, if we fully prime factorize that, 2 to the negative first power times 3 to the negative first power. This gives us 1 times 2 for our next transformation, leading us to the number 2, which we know leads to 3 and 4 and stays fixed there. What about the number square root of 6? Well, the number square root of 6 ends up being 2 to the power of 1/2 times 3 to the power of 1/2. Once we transform this by adding the primes to the exponents, we get 2.5 times 3.5, which is 35/4, and that gives us a prime factorization at that stage of a 5 to the 1 times a 7 to the 1 times a 2 to the negative 2, And this 2 to the negative 2 adds to a 0, which sort of crashes the whole thing to 0 when we multiply. We could even use cube roots, like the cube root of 6 can be prime factorized as 2 to the power of 1/3 times 3 to the power of 1/3. When we apply the transformation here, 2 1/3 times 3 1/3 is 70/9, which has a prime factorization of 2 to the first times 3 to the negative second times a 5 to the first and a 7 to the first. And then we'll go to wherever this leads us. We can notice that rational numbers that aren't integers will lead to an integer after at most one step, and that these root forms of numbers will lead to some form of fraction after at most one step, meaning that these root type of numbers will lead to some integer after at most 2 steps. This gives us an even bigger set of numbers that we can input into this type of transformation and either get one of the positive cycles that we're used to, the number 0, or the negative version of one of those positive things. Now, what about other similar transformations we could apply to numbers? There are also many other ways we could extend this general concept. In my head, I used the term Primeglitching to think of the general concept of taking a number, taking its prime factorization, and then doing some alteration to each component, like replacing each of these components with some new mathematical expression related to the two variables in it. Like we had been adding them together for our main pattern today, but I've experimented with a variety of other things, from just flipping them to taking more complicated mathematical combinations of these two variables for each aspect of a number's prime factorization and iterating it. And I've already found some other cool patterns, but this episode has already been super long, so I'll save that for another day. And if any of you want to do any of your own experiments, let me know in a comment what you find. And that's probably enough for today. Thank you for joining me to learn about some interesting number sequences and other things like that. I'll catch you in the next episode, and let's give a special thanks to all the people who help make this show possible, such as my Patreon supporters. And I love all of you. I'll catch you again for next episode, which is actually the finale of grade -2 before we move to grade -3. And I hope you have a good one.